Thanks, Iman. Many thanks. For this presentation, the order of my slides might come as a surprise to me, since we have had a little change of the organization. So I will mainly present the role of general cognitive ability in brain reserve and maintenance, but I also will provide some further context also relating to Lash's talk on education. In this case, general cognitive ability, just in case some of you here are not psychologists and are not so familiar with the concept, this is likened to what people call intelligence. And when we talk about intelligence, it's always adjusted for age. So in that way, it's stable. But of course, the raw scores that underlies this score, they change a lot with age, as we can see here. So you have a lot of age differences in the actual performance, but you also have a lot of individual difference irrespective of age. And we can see this dispersion that is, it seems to increase the individual variability here. So, but intelligence is associated with all-cause mortality and health, a number of lifestyle factors that are known to affect brain health as well. And it may relate to brain characteristics bidirectionally, of course, also through correlated exposures, such as education, such as income, and things that are associated with that. But a number of studies, as reviewed by Derry and colleagues, actually have found that there are associations between general cognitive ability and health, also when you control for education. And I think that's the interesting part here. So there have been a number of proposed associations so that both education and income can affect the brain and general cognitive ability positively by these different exposures. And one thinks that brain development may be boosted, but also atrophy may be diminished. And cognitively high functioning people then may grow greater brain reserve to begin with, and they may age more gracefully, have less atrophy, so they have greater brain maintenance, as we heard from Lars also. So, but what is the evidence for these claims? So in Lifebrain, I think we have focused a lot actually on these claims. So there are a number of papers, including the one that Lars just presented, but also work in progress by Ole Rødberg and colleagues on the shared data. And we have these other two papers. I'll just briefly touch upon the first one now on education and income and how the relationship is actually quite heterogeneous to general cognitive ability and brain characteristics across European and US cohorts. And then I will end up talking about how brain aging actually differs with cognitive ability regardless of education. So if we look at this first thing we did in Lifebrain, to begin with, we just wanted to look at the associations of education and income and general cognitive ability across European and US cohorts across the entire lifespan from 4 to 97 years of age. And here we included the UKB. So we have 54,000 with imaging in these analyses. And as you can see, and this should be no surprise, this is cross-sectional data. So general cognitive ability is related to cortical volume and area, as we know from beforehand, across much of the brain. But this also is true for education. With more education, more volume, right? With higher income, more volume, and so forth. So what does this really mean? I think we need to really be aware that these relationships are very heterogeneous, and it really depends on what cohort you're looking at. And these cohorts are also, to varying extents, representative of the nations or the societies from which they come. But I think it's just good to be aware that there is significant heterogeneity, so that income and education in some of these cohorts, they are very strongly related. In others, they are virtually as in some of the Scandinavian cohorts, for instance. And then when it comes to cognition and education, this variability also holds, and the same is true for general cognitive ability and income. So that, I think that's just useful background. And if we look at the neuroanatomical volumes, we see the same heterogeneity Intracranial volume, for instance, is moderately or weakly related, positively related to education, but there is a lot of variability. The same goes for gray matter when we control for intracranial volume. And we see that it's significantly more strongly related in the US cohorts, ABCD and HCP in this case, than in the European cohorts overall. So these effect sizes that we have here, this is work by Andreas Brandmeier, who did the meta-analysis on top of these Spearman correlations, where what we enter is adjusted for age and sex. So I think it's just important to keep that in mind. The same goes for income. Actually, it might not be related at all to the brain volumes in some cohorts. In others, you see a much stronger relation. Because these are things we want to control for in our analysis, and that will actually have very different effects depending on what kind of cohort you're talking about. So the same actually, to some extent, goes for general cognitive ability. It's variably related to neuroanatomical volumes across European and US cohorts that we've been looking at. But overall, general cognitive ability is positively, but I would say quite weakly related to neuroanatomical volumes. And intracranial volumes, they tend to show stronger associations to general cognitive ability than to gray matter controlled for intracranial volume. So this suggests actually that these relationships, if anything, they are established early in life, because intracranial volume is virtually almost as adult at, starting with school age. So I think that's also important to keep in mind. So when we're talking now about the role of general cognitive ability, I just want to say where I come from, because I have a very much early life focus in much of my research. And a number of studies have found that higher general cognitive ability in young adulthood is related to lower risk of neurodegenerative disorders in older age. But the mechanisms are really unknown. But I think that all of us studying the brain, we need to be aware of whether we're studying that in a 90-year-old or in a 7-year-old. We're studying a system that was mostly made in the womb, actually, because a lot of brain development goes on in the womb, and a lot of processes are actually exclusively prenatal. We have very little neurogenesis after birth, if anything at all. And so these factors that are influencing us at this time will likely work for a lifetime. And we need a lifespan perspective on these early life influences. So what influences are at work when? So we've seen these proposed explanations, whereby some people may have, let's say it's just gross brain volume or gray matter volume or whatever. They may start out with the same, and some maintain better than others. And so they will fall below this functional threshold cognitively later than others. But the alternative explanation is just that we start out with different amounts of resources, and we can age exactly the same, but we will still end up falling below this functional threshold at very different ages. So, and that is brain reserve, and whether you call that passive, you can call it passive in this regarded one, I think. So, but there could be multiple explanations. So as a background for this study we did on whether general cognitive ability actually relates to brain aging or brain atrophy in aging, I think this is useful background because a lot of our cohorts, they are recruited from the mother-child cohort study in Norway. And so we have early life information on them. And in this case, we had 1,000 persons in the age range 4 to 88 years, and most of them were scanned multiple times. And so we started out by just relating general cognitive ability to cortical area, because that's what it's most strongly related to in the child cohort. And we found that, well, there were significant relations across most of the cortical mantle, cortical area. And then what we did next was that we took this area related to general cognitive ability, and we split the sample, the full lifespan sample, in two, the upper half and the lower half, and we mapped this for the two groups throughout life. And then you find the expected effect of age, because cortical area increases until about age 13, and then it starts decreasing, but very little. And we found what's interesting here is that these slopes for the higher and the lower half of the sample in terms of general cognitive ability, they were completely parallel. And we actually were able to test this, that they were not different. And there is no age interaction. And we found that what this here was related to, the extent of area here, we had the early life factors. We found that there was the only thing that related to this was actually birth weight, not parental education, not parental income, none of those factors, but birth weight, whereas parental education related to general cognitive ability. So I just wanted to say that that was important background to me, and sort of that speaks for, I would say that what you have early on, it determines a lot of what happens later, right? So that was area though. So I was actually kind of surprised when we were investigating how general cognitive ability relates to cortical volume area and thickness change altogether through the lifespan, because we wanted to understand this association between general cognitive ability and dementia risk. And here we used both Lifebrain and UKB, altogether 7,000 MR scans, and it's the adult age range. So it's a meta-analysis. So first of all, the level associations across Lifebrain and UKB. We first did the analysis on each cohort and then the meta-analysis. So we can see the expected association between level of general cognitive ability and cortical volume and cortical area, and nothing for thickness. That was expected. But when it came to the level change association, we actually saw that baseline general cognitive ability related to change in cortical volume. So that those with higher ability, they had less volume loss, and they also had less cortical thinning in these areas. That actually came. And when we look at these, because this is an age interaction, right? So this is an interaction of time, right, with general cognitive ability, not age, but with time. And we see that actually it's quite well ordered in the UKB and Lifebrain, so that those with the higher general cognitive ability, they have lesser cortical volume change and lesser cortical thinning. It's extremely well ordered in Lifebrain and UKB here for volume. For thickness, we see a little bit of both, but I think that's interesting. And then we tried actually to just control in UKB for polygenetic scores for effect of, for education and for general cognitive ability, and actually these effect maps, they changed very little when we controlled for that. I'm not saying that then it's not the effective genes, but that was the best we could do. That was sort of interesting. And then we asked whether effects on general cognitive ability or general cognitive ability and cortical change actually change with age. So this is a three-way interaction, and actually it came out significant here in the left hemisphere across UKB and Lifebrain, but I would say these are very restricted areas, right? So in all of these analyses, we controlled for education. That was the point. So it comes out and as significant. And what we see with this three-way interaction is that we can see that these trajectories for the different general cognitive ability groups, they do depart more in higher age after age 60. These are just illustrations of the effects. I'm just emphasizing that. But you can see that that is actually the case here to some extent. So that's interesting. So to sum up, I want to emphasize there is no uniform association of socioeconomic status, brain and cognition across different cohorts. You need to know the cohort you're looking at. We find that the brain and socioeconomic status relations must be established early rather than in adulthood based on the differential associations of intracranial volume and gray matter. And most of the brain general cognitive ability relations seem to be grounded in intercept rather than change effects, but there is somewhat less cortical thinning in aging with higher general cognitive ability, and hence also this has an effect on volume. And there is then a possibility, we think, that factors associated with increased general cognitive ability, other than education, which we controlled for in all analysis, and possibly genes, which we can't control for. We can't do Mendelian randomization in this very small sample, but we had the BTSs. Maybe such factors could serve to diminish cortical atrophy in aging, but we don't know what they would be. But since childhood general cognitive ability is highly predictive of general cognitive ability in aging, We think that they likely, as with income and education, work at developmental rather than adult or aging stages. So thank you.
Thank you, Kristine. And I think it's really exciting that we now actually got to a finding where we do see some individual differences in change